This is the Lexington High School Robotics Group. This is the STAR. This is the device that they have designed and built, and we're going to talk to us tonight about what went into doing that.
First, let's all introduce ourselves. I'm Kriti Mugawa. I'm a junior this year in high school. This is my third year on the team.
I'm Anhad Sani. This is my first year on the team. I'm a sophomore.
Hi, I'm Jesse, and this is my third year on the team.
I'm Arjun, also junior, also my third year on the team.
I'm Mike, I'm sophomore, it's my first year on the team.
I'm Noor, I'm a junior, this is my third year on the team.
I'm Jennifer, I'm a sophomore, and this is also my first year on the team.
I'm Neil, this is also my third year on the team.
I'm Kevin, this is my third year, and I graduated 2 days ago.
Congratulations! Welcome to the scary real world.
All right, so we're 2 Bits in a Byte. We're a robotics team that participates in the First Tech Challenge. We were founded 9 years ago at Lexington High School, and we're completely self-funded, meaning that we raise all of our own money, and we don't take anything from the school or the town. So what is FIRST? FIRST is an organization that seeks to encourage kids like us to get into STEM, and they have competitions for grades 3 through 12.
Okay, so as part of the First Tech Challenge, which is the program we compete in, we're strongly encouraged to do a lot of outreach. There's a lot of advancement opportunities in the competitions, and just a great way to spread STEM. So a few of the things we do is we try to go to a lot of local events and let kids and parents talk with them about STEM careers, and also let them drive the robots around. So recently we went to the Boston Mini Maker Fair, the local Lexington Discovery Day, and the Birthday Wishes Cakewalk, which is a charity for underprivileged kids. We also try to talk with a lot of professionals in the field. So recently we toured Ava Robotics, which is a telepresence company, Mass Robotics, and iRobot. And we got a lot of chance to talk about the careers in STEM that some of us might be interested in, especially in engineering. And another thing that we do as a big part of our outreach is just trying to teach kids robotics. So the biggest thing we do is we have a rookie program, which takes underclassmen from our high school and teaches them the basics of robotics. And we have classes with them, and then we have a competition at the end of the year. And this is a great way because to teach kids about engineering, because there is only one engineering class at our high school, and it's only for seniors. And we also started teaching started teaching at a local recreation center, Hayden, to teach elementary schoolers and middle schoolers robotics.
So we have some constraints that are put on the robot. They play a really big role in how we design a robot and the different designs that we choose to use. It must fit within an 18-inch cube. It has to be under 42 pounds. All the power has to come from a single 12-volt battery, and then we can only have 8 motors and 12 servos on the robot.
What's a servo versus a motor?
So the difference between servos and motors are these bigger actuators that you can see here. We don't have precise control over the actual angle that the motor is at, but we can control its speed and we can measure its rotations. With servos, they have a limited range of motion. They're also weaker and slower, but we can get really precise at which angle they're turning at. Okay, so this is our drivetrain. It consists of the 4 wheels and the motors that drive them. This is the part of the robot that most teams will actually try and build before the competition is announced, because it doesn't change a lot. One thing about this competition is that it had the elevated crater walls in each corner of the field. So those were hard to navigate over because they were a big obstacle in our way. So that's why we couldn't actually build our drivetrain ahead of time. Because we had to elevate it a couple inches off the ground to clear those walls, and we couldn't anticipate that. Okay, so for our drivetrain, we use a holonomic drive. This is a unique system of movement, which basically means that every available degree of freedom is able to be independently controlled. So what that means for driving in 2 dimensions, we have 3 available degrees of freedom. One is our x-coordinate, one is our y-coordinate, and one is the rotation that we're at. In theory, for each of these degrees of freedom, you would only need one motor to control them, so that's 3 motors total for the drivetrain. And there are 2 systems that accomplish this, as you can see here. The problem is that one of the major constraints in our robot is that we have to fit inside an 18-inch cube. So that means it's best for our drivetrain to be a square shape. The problems with these ones is this one is triangular, and then that one has a motor in the middle, which is taking up valuable space. So that's why we didn't go with those. The system that we used actually consists of these specialized wheels called Mechnum wheels. So the unique thing about these wheels is that they consist of a set of tapered rollers like this. They're all mounted at a 45-degree angle. The important thing about these rollers is that they're pretty grippy. So in one axis, they can roll freely, which is the free axis, and then at a right angle to that is the restricted axis, which prevents movement. Once you combine all of those rollers and you put them on a wheel, that means that when you turn the wheel forwards, the robot actually, or the wheel moves in a diagonal vector of movement like this, and then at a right angle to that is free movement. So the main advantage of a holonomic drive is agility. We have a very limited amount of space to work with on the field, considering that there are 4 other robots and then all of the structures actually on the field. So that means we basically have to be able to turn on point and then move in any direction that we want to, like on demand. So here's a good example for that. This would be parallel parking if you have a holonomic drive. You can see it's very simple. You just reverse in and then translate at a right angle to that. And then this is parallel parking with a regular car. As you can see, it's a lot more complex. An important thing to note is that driving with a regular car, even though you can be at any location and you can rotate, the car actually has a non-holonomic drivetrain, because when you want to make a turn, you often end up moving to a different location while you're executing that turn, which obviously wouldn't work for our robot considering the space constraints.
Do you lose points in the competition if you bang into another robot?
You actually don't, but there are specific rules about how defensive you can be and how much you can interfere with other robots. Okay, so when you combine the diagonal vectors of all 4 Mechnum wheels, you can achieve basically the 6 basic motions in 2D space. So first off, the most simple one is when all the wheels are going forwards. Even though the diagonal vectors of movement for each wheel are pointing in different directions, the end result is that the whole robot moves forwards. Then by flipping the directions of 2 of the wheels, we can achieve the more complex motions. So for example, if the wheels on each corner, on 2 of the corners move in reverse, we actually translate left and right. And then in the last configuration, we can rotate in place.
Run down the aisle, maybe? Everybody can. Run down the aisle, maybe? Everybody can.
We also learn a lot about other skills that we should know in life. The first one is communication. We have a 15-member team. This isn't even all of us, and we all work on different parts of the robot. And so it's really important that we all know how to communicate our ideas and goals and deadlines throughout the season. The next thing is goal setting. We have a 7-month season, and we try to set long-range goals and then break them up into smaller tasks that we can keep track of. The last thing is collaboration. We, again, have 15 members. And so we kick off every year with a sticky note meeting where everybody brainstorms different solutions to the challenge that we've been given. We decide on the path forward through different meetings with everyone where we weigh the pros and cons of all the ideas that we have.
So there were about 8 seniors during this season, including myself, and we'll all be going to college this fall to study a STEM-related field, whether that be biology, chemistry, mechanical engineering, electrical engineering, computer science. We'll all be studying what we really want to study in college, which is very respectable, in my opinion. So I chose to do mechanical engineering at NYU starting this fall, and I'm possibly a minor in computer science and electrical engineering, which I'm very, very excited for. So other than NYU, other schools that this year seniors are going to attend are UIUC, Purdue, UMass, RPI, and Northeastern.
2 bits and a byte.
We're done?
I think it's done. Okay. So hi, here. Wait, where do you shear? Sheared right here.
Yes. That's